That way we're little. Yeah, so where it says trial 1 and it says length of Twizzler, just go ahead and measure that. Yeah, and measure in your centimeters. Awesome. Okay, so exponential growth and decay. We are now learning where we've been taking all of our different functions, right? We've had lots of different exponents. We were learning in chapter 7 about all of our different rational exponents. So where we had things where we had x raised to the 1/2. Remember, our fractional exponents really just mean that it's a root of some kind. So we rewrite those. So we learned how to graph roots. We would learn that the roots were the exact opposites of our regular exponents. And so we graphed along what line? What was that identity line that we made those inverses? Do you remember what? Yeah, and it was called y equals what? Y equals x. Yeah. So when every time that x was the exact same as y, it formed that diagonal line. And so now instead of flipping along a y-axis or flipping along an x-axis, we're actually going at a diagonal. So it took everything that was facing upright and it made it go sideways, correct? So we have consistently seen that we always have things that are pairs, right? I talked about that a little bit last week in our class where addition has subtraction, multiplication has division, exponents have roots, and so now we have this new pair that we are learning about in chapter 8. And it is our exponential equations and logarithms. And so even though we start learning about the parts differently, when we can think about the fact that there's a pair, this is going to have a pair, it's going to have to go together, then we can start putting those pieces in and then leave a little marker of, here's my first one, I'm going to need a pair to come along the side of it. Okay? Our pairs work the same because we're still dealing with exponents. And we know that from exponents, everything that was upright was turned sideways when we have a graph. So it's going to work exactly the same with this set of pair. But instead of our variable being in the bottom, we learn that our variable is now in the sky. Okay? So we flipped places of where our variable was. And graphically, what that changes is instead of having a graph that maybe goes up, you know, with a parabola on both sides or has an S-curve if it's a cubic, is that now we are going smaller and smaller and smaller in one direction and bigger and bigger and bigger in the other direction. Now we go. And it is confined to one side of our graph for our coordinate plane. So if we have an exponential growth, it looks like that every single time. So we're getting closer and closer and closer and closer to 0. So this is getting smaller as it approaches our x-axis. And then we're growing away from the x-axis right here. So if we had a straight line, remember when we had all of our little pipe cleaners that we could bend? If I had a straight line at x, so y equals 1, so I had my little straight line here, and I want to start growing this away, all we're doing is we're taking this line and we're bending it. We're taking the end of it and we're going to leave our point here. We're just going to keep bending it. We're bending it up. We're making it move away from the x-axis. Okay? So then we have to think, what would our inverse do? Our inverse is going to move away from our y-axis. right? Okay, so start plugging those things in. As we're moving away from the x-axis for our exponential, for logs we'll move away from the y-axis. Okay, so even though sometimes we have negative, we had like a negative 2 to the x, so our base here is negative, and our graph went down because it's negative. It's a negative slope. It's still moving away from that x-axis. Do we see how it's moving away? That direction. So when we're moving left to right, we read left to right. In math, we're going to go left to right. Both of these are exponential growth. It's hard to think of this negative one as growth, right? Because you're like, it's getting smaller. But as you're moving, it's growing away from that x-axis. So in 8.2, we discussed exponential decay, which is exactly the opposite. So let's logically think about it. If growth is moving away from the x-axis, then decay would be moving towards the x-axis. So from left to right, we're going to be getting closer. So from here to here, we're going to get closer and closer and closer. So now we're moving towards the x-axis for decay. We start somewhere and we're getting closer and closer and closer towards it. That also means if we have a negative 1 and we're coming from the bottom, this looks like growth. I mean, if I'm looking at it, I'm like, oh, it looks positive, right? But what is it doing? We are going from left to right and we are getting closer and closer and closer to the x-axis. When we are growing towards the x-axis, we are looking at decay. Okay? So algebraically, when we're looking at our formulas, when we're looking at our equations that we have, there were two things that were major identifiers that we could look at it and immediately go, growth or decay. Growth is everything bigger than what number? Do you remember?
1 or 0.
Growth is bigger than the number 1. Okay? Decay is less than the number 1, but greater than 0. So we're still dealing with positive numbers. Remember, negative numbers just flip the whole side of it. But so we're looking at either greater than 1, or we're looking at fractions, basically. Anything that's less than 1. So 1/2, 1/4, 0.25, 0.1. So bigger than 1, but bigger than 0, but less than 1 were our decay values. We're getting smaller and smaller. We don't have an equals 1, right? Because when y equals 1, we just have a straight line, right? So this is where we're starting. Our equals 1 is right in the middle, and then we get to decide what happens. So if it gets greater than 1, it's going to push. I wish we had our little bendies. It's going to push this up. If it's less than 1, it's going to push it closer. So our pipe cleaner or whatever would move according to like growth. We're going to get bigger. Decay, we're going to get smaller and closer to it. Okay. Does that help understand the growth and decay? Any questions about those specific items? Okay. Our graphs, our base now has that very special number. So I put this up, and I think I have a sheet that I know I had a slide that talked about this. We've been learning all along that it's our m value, is our slope. You guys have been seeing an ax plus b, right? So we had an a value for our linear equations, an a value for our quadratics, an a value for our cubics. We've had a values for roots, and our a value the entire time has told us steepness, right? Slope, steepness. We are able to look at it and go, oh, that's a 2. It's going to be steeper. Now, because we have swapped where our exponent is no longer in the top, but our variable is actually in the top, so now we have 2 to the x. Since we swapped that, we are swapping what our values mean. Okay, so that's just an easy way. I'm like, if you switch one, you got to switch the others. So now that any extra number that is in front is now our y-intercept, instead of having our y-intercept tagged along here on the end. Okay, so it is now our y-intercept, or our starting place where we start at. Okay, and our base tells us the rate at which it grows. So that's kind of your steepness. That's your slope point of it. And we talked about why is this number important in now our y-intercept. And why do we always start at 1? Like, why is it not going through the origin? Well, first, our x-axis is called our asymptote. That very hard to spell word. Asymptote. And this just means a boundary line. Like when you're a kid and you're like, don't you dare cross this line. You know, don't put your toe up, and you're like, I'm going to get as close as possible. So that's your asymptote. It's going to get as close as possible to this, but it will never, ever actually touch it. Okay, it's the boundary line that your graph has to stay on the other side of it. So our asymptote for all equations that are exponential equations, it starts at 0. So that's why our value can't be at our origin, because our boundary line is those positive numbers at 0. So if we started at 0, could we get closer and closer to the 0 line? No, we can't. Also, we learned with exponents, we had some special rules. If I gave you 4 to the 0, that equals what? 1. Any number raised to a 0 will always equal 1. So let's go to our equation. We have a base, any base raised to an x value. When x equals 0, so we're looking at our origin spot, we're always going to ask that question. When x equals 0, what is y? When x equals 0, no matter how complicated this section is, it turns into the number 1, right? So if this whole thing turns into the number 1, 1 times your coefficient is simply the coefficient. So every time x equals 0, y simply is that coefficient. So we have this point when x equals 0, y is equal, this is an unwritten 1, y is 1. That is why for our exponential graphs in our basic form, we always have the point 0, 1. Because we're answering that question, when x equals 0, what is y? What was great is that we were able to learn that we can take our basic formula that we've always had. So now our new one is this. Y equals b to the x. There's really a value in front of that, right? And we can start adding stuff to it and changing it and adding stuff that we already know. And it doesn't really change a lot, right? I can add an h value, and anything that I add to an x does what to the graph? How does it move it?
Oh.
Side to side. It moves it along the x-axis, right? Our h value, we have h and k, same thing. So this is what's great about it. Like, if it worked for quadratics, it works here. It's the exact same thing. Anything that we have for an h value is going to move on our x-axis, back and forth. If we add some k value onto the end, it does what to the graph?
Moves it up and down?
Moves it up and down, yeah. Because the k value has always been your y-intercept, correct? When this whole section is 0, y equals k, right? So it moves it up, down. So now we took our basic formula of y equals b to the x, and we added maybe a different place that it started. We've adjusted it along our x-axis. We can adjust it along our y-axis. Then our base decides to either grow or decay. So we took our base and we said we always start with 100% of what we have. So we moved in and we took our basic equation, and part of your homework was using it for interest. That's the most important thing that it's used in every single day. Anybody have a bank account? Okay. Anyone have a car? Do you have a loan on your car? Did you pay cash for it? Okay. You're well acquainted with interest. In your bank account, you want your interest to be high. For your car loan, you would like your interest to be low. Correct? It matters because interest pays us back. So where does that tie into our equation of exponential growth that we have? It's the rate. And we can do that. They say you have a 3% APR, annual percentage rate. So when we think of our base as a rate, that's the rate at which the graph is changing. Oh, that's pretty cool, isn't it? Then we can break this B up into something different. We can say, if I have 100% of what I have, you give me 10 bucks, I have 10 bucks, right? I have 100% of what I have. If you start adding something to what I have, 100% is the number 1. If I start adding something to it, where does that fall in my growth or decay? If I'm adding something to my number 1. So I'm starting at 1 and I'm adding it. It's going to make it greater than 1. So now all of a sudden I have growth when I'm adding something to it. If I start with 100% and I start taking stuff away, I now have 1, my base 1, and I'm taking things away, so now I'm going to be less than 1. So that ends up being decay. Do you see how our base can easily change to growth or decay depending upon whether we're adding something? Adding to what we start with gives us growth. Taking away gives us decay. We're getting smaller and smaller on it. And we learned the different rates that we could add to. So we started from something very simple of just our y equals b raised to the x. And we were able to add all of these extra values that just change the graph a little bit. But it all works in the exact same process. Does that make sense? Do we see how it's all tied together and it's not actually different items? Okay, so we're going to do our little lab to look at this. You have your Twizzlers with you, and on the Twizzler lab, it talks about trials. So we're going to actually cut our Twizzlers. There should be some more scissors. You're going to you measured your Twizzler already, and then you're going to figure out exactly where you need to cut it. You're going to cut it in half, and then you're going to measure it and put it in trial 2. Okay, so keep cutting your Twizzler until you cannot cut it any smaller. And then you can use your boards to start graphing what you have. Extra boards.
So keep cutting it.
Yep, so keep cutting it in half.
Yeah, I actually forgot my cable sheet.
Oh no.
I also did that. I only have the first page too.
I don't know, and I was gonna print them for you guys.
I have an extra.
Why don't you just make a chart? You can use it just any sheet of paper. All you need is a chart. And you can transfer it when you get home.
So we just keep cutting it in half?
Yeah, just on the back. So you just need a chart that's just like trial 1, 2, 3, 4,
Okay.
however many, and then your length on it.
Like the length
So, for like trial 2, for instance,
Uh-huh.
would we, like,
So trial 1 is the whole length,
and then trial 2 is half
is the
of
length, yeah, what is that length now?
10.
Okay, so write that down.
And
Well, yeah, and then cut the neck, cut it again. Hopefully it's that, right? I mean, if you cut right. And then on your board, you're gonna mark 1, 2, 3, 4. These are gonna be your trials.
Are we supposed to be able to make it to trial 10?
No, maybe not. I mean, if you're folding paper, you can only get to 8, right? Cut them as small as you like.
do you want us to do like each
No,
one?
just one
Okay.
thing. Okay. So then once you have a good 5 or 6 points, you can start plotting your points on the graph. Perfect. And since we didn't start with 0, will your graph touch the y-axis? Since we don't have an x equals 0? No. Now, had I said put x equals 0 as the length that you're at, and then trial 1 was the first time that it was cut in half, would it have touched the x-axis at that point? Yes, it would have, because we would have put that initial starting point. So understand that if you're looking at your graph and it's not starting on the y-axis, it's just because we started at trial 1 instead of saying, here's my starting point. So again, you could technically shift your whole graph back. Okay, so there's some questions after this. It says, as you're plotting it, what does your graph look similar to? So from what we were just learning, what does this look similar to? And why do you think it's true? So from the graphs that I was putting up on the board, does this look similar to something? And if you took your data and you wrote an equation for your graph, what do you think your equation would be? Remember, here is our original. If you think it looks like an exponential equation, what would these numbers be? What do you think your graph would be? And think about what you're doing. What did I ask you to do every time to the Twizzler? How were you to cut it?
Half it.
You were to half it. Okay? So each time, were you taking 5 off of it? No. You were taking a different amount off every single time, but that amount was proportional to what you had. Okay? So that value is this rate of change. Okay? So that's the difference when we had x squared versus 2 to the x. Okay? Or x to the 1/2 and 1/2 to the x.
So the 2 means that it's doubling?
Yes, so if we had x squared and 2 to the x, our b value is now, what are we doing? Not, I'm taking a random number and I'm specifically doubling that. No matter where I'm at, I'm always going to double it, right? So if I have 4, I'm going to double it. If I have 10, I'm just going to double it. What this is now saying with our new bases, with our exponential growth, is that in relationship to what I have right now, that gets doubled. Right? So if I have 4, I'm going to add 2. If I'm doing more, if I had 10, I would be adding 5. Right? So we're adding different amounts. When we have our original quadratics or cubics or whatever, every time our number, it's the same every time. The greatest way to look at this is to have a chart. So if I have 1, and we just start with 1. So this is 1. Let's do 3. Okay. 2 squared is 4. 3 squared is 9. 16, 25. I have 2, 4. Oh, it's looking the same. 8, 4. It's hard when we're looking at the squared and the double, when you're like, oh, it's just kind of doubling. The squared is kind of doubling again, right? But as we look through, what starts happening? If I have 6 squared, I'm going to end up with 36. But if I double 32, I now have 64. Okay? So our rate at this one is dependent upon our base, and we're squaring it. So it's that nice parabola, and it's growing up. But whenever we have a base, it's doubling in relation to whatever one we pick. So as we get bigger, then our doubles are getting bigger. So it's exponentially growing. So for your graph with the Twizzlers, what did it look like? Did it look like growth, or does it look like decay?
Looks like decay.
It looks like decay. Why does it look like decay?
Started up high and started going close to the x-axis.
Started high, and it's getting closer to the axis, right? It's moving closer. Perfect. So it's automatically decay, which means that our b value has to be less than 1. What do we think our b value is? Perfect, Tessa. Half. Because every single time, regardless of where we started, we weren't taking off the same amount. At the beginning, you took off a lot more than you took off at the end. However, in relation to what you had, it was still 1/2 of what you took off. So your equation for your Twizzlers graph would be y equals 1/2 to the x. You would be able to write that. Okay? We're going to use some M&Ms to look at growth.
How do you graph?
What?
Well, like take the points, how do you graph it?
How do you graph your actual points?
Yeah.
So for trial 1, you would have, what was your length? Yes, so for trial 1, which I was talking about, technically your first length is your x equals 0. It's your starting point. So you would start at 0, 20, whatever. And then your first cut, you're at 10. Your second cut, you're at 5. Third cut, you're at 2.5. Fourth cut, there we go. And so we're just getting closer each time. Does that make sense? Okay. So if we took that and we said my A value has to be my starting point, what would we put for our A value? The length of the Twizzler, right? Were you guys all pretty close to 20?
Yeah.
20 centimeters,
20.5.
something like that. So we would start, so a true exact equation would say I'm starting at 20 centimeters long and I'm halving it every time. So if I said, how long should your piece be after 4 cuts? After 4 cuts, where would the 4 go? What is the 4 value? That's your trial. That's your number of times. So 4 replaces our x. It's the number of times we're cutting it. So after 4 cuts, I would have 20 times 1/2 to the 4th. 1/2 to the 4th is same as 1 to the 4th over 2 to the 4th. See, this is why we had to learn our exponents rules first, right? It gets distributed. 2 to the 4th is 16. So I have 20 divided by 16. Plug that into your calculator, Josh.
1.25.
1.25. Is that pretty close to something on your trial for 4? It might be 5 on yours since we started at 1. Did you have a 1.25?
Yeah, 1.
Might be a little bit over since you started. Yours was a little bit longer.
Yes, it has a.
Yeah. So we were able to actually graph it out, or I could predict and say, after 4 cuts, your piece is going to be 1.25 centimeters long. Right? So M&Ms, if you don't have your papers, make another chart. All right? And it's actually, your first one is K. It's actually, if you have your papers, it's the second page for it. Okay? And so we're going to start with 2. You can take your M&Ms. We're going to start with 2 M&Ms.
This is the same page.
Yep, right. Here. Okay? So it says put 2 M&Ms in your cup. You can pour your M&Ms out onto your paper. So we're starting with 2. What value of our equation is that? Our starting value? A. So we're starting with 2 M&Ms. Okay? 2 M&Ms in the cup. Roll your M&Ms out. Okay, and you should be able to see if there's one side has stuff on it. So just pour your M&Ms out. Pour out there 2. Okay? And add 2 M&Ms for every M&M that has it facing up. So currently you're at 2. If you roll them out and neither of them are showing the logo, then you're not going to add anything. And you're going to do for trial 1, see it says Sue, for trial 2, it says add 2 new M&Ms for each one with an M showing, and then record the total number of M&Ms that you have currently. So if you have 0 M's showing, you might still have 2 as your second one. We can actually change this to, so for trial 1.
Can we erase the Twizzler graph?
Yes, erase your Twizzler graph, okay? So pour your 2 M&Ms out. Okay, so then trial 2, you still have 2. And then do it again. Okay, so do it again. Okay, now you have 2 showing. So for every single one that's showing, add 2 M&Ms. So now, yep, you have 1, so you're gonna add 2. Add 2 M&Ms for each one, so now your total is what?
Wait, the total of.
Yeah, now 4. Okay, now put them all in your cup. Okay, so
Well, I got that, but like, where do you start writing?
we're gonna start, so this was trial 1, you have 2. So now you have 2, you need to add 2 M&Ms for each M&M that is showing. So add 2 M&Ms here.
It's supposed to be right in this one.
Yes. Add 2 M&Ms for this one. Now, how many M&Ms do you have total? Yes. Now put all of those in your cup and roll it out again.
Oh,
Okay. Now for everyone that gets rolled out again. Okay. So now pull those aside. So for each one that's showing, you're gonna add 2 more.
Add 2 to the.
No, yeah, so you need to add 2, 4, 6, 8, 10, 12. You need to add 12 M&Ms. Is that making sense? Okay. You getting it?
yeah.
And then total them all back up, and then put it back in the. And I have more M&Ms. We need more M&Ms. And a couple of bags. You need some more? Okay. I do want you to have at least 5 trials. Okay. Need some more M&Ms? Okay. So think about what's happening. Okay.
I'm getting more.
Okay.
I think. No, it's gonna be fine. I'll do it now.
Said 5 trials.
Yeah. You good?
So you ever have a number of M&Ms that like has the increase in height?
Okay. Yes. So for each one. So when you rolled these 2, okay, if you had, you would write 2. So now this one's down, this one's up. So I'm going to add 2 M&Ms to it. So now I have a total of how many? 4. So that would be 4. So now we're going to roll again. Roll again. Now up, up. Oh. So now I need to add 2, 4. I'm going to add 4. Because I'm adding 2 for each one, right? So now I have a total of 8. Okay. So that's your third one, 8. So now roll that again.
There's so many.
Okay. That one was that. Yeah. So how many do you add now?
Just doing hypothetically.
6.
I'll have you more of
So
that.
how many do you have now? Do you need any more M&Ms? You good?
Yeah, I need more.
Okay. Do you have enough to make it?
Oh, yes.
Perfect. Okay. So look at your data now, and let's decide, is it growing or is it decaying?
It's great.
It's growing. Okay, let's start plotting your points. So you should, where did we start? We started at trial 0. Spell. Trial 0 is going to be your 2. So everybody should have a point at 0, 2. Should be your very first point. I know on there it says 1, trial 1. Put it at 0, 2. Just move it back up. So this is going to be 0, 1, 2, 3, 4, 5, 6. Do you need some more minutes? You good?
No, I'm good.
Okay. Now you can eat your M&Ms. Do you need some more?
Can we eat our Twizzlers?
Yes, you can eat it all.
Wait, did we have to make it tonight?
No. I said 5 or 6.
My first started off slow.
Well,
Good.
there you go. Miss Lowe, do you want any M&Ms? I'm good, thank you.
What'd you end up then?
I love M&Ms.
But I didn't actually have 54 inches. What did you?
94.
So when we did the Twizzlers, everyone's graphs looked exactly the same, correct? A couple of us started in a little bit different place. If the Twizzler was at, a centimeter longer or so. But they all looked exactly the same. So let's graph what we have now and see what that looks like. And you might have to turn your graph sideways since you need to go up further. Since we need more y values. And you can do your y values by fives. 5, 10, 15, 20, 20, or whatever.
You said you wanted us to start at
0, 2. Everyone should start at 0, 2. Because where we start, our starting value was 2. Right, so our y-intercept is always our starting value, because if x equals 0, then that whole part of the equation equals the number 1. So 1 times your starting value is your starting value.
So we're going up like this.
Mm-hmm. So then you would be at, this is actually 0. That's what I want you to do. 1, 6.
You're putting upside down so fast. Okay,
So 1, 6. Yeah, and you might have to count by 2s on yours since you go up pretty
by
high.
twos or by fives.
Doesn't matter.
Okay.
Count however you want. You'll see where it starts
I
going.
did it by tens, so.
Perfect. There you go. So everyone's graph should be going up. Let's think about what changed in this experiment versus our Twizzler experiment. It was going up versus going down. We know that. But what was something specific about the instructions? With the Twizzler experiment, you
We're halving it.
you had to half it.
There's no constant rate of change.
There's no constant perfect test because it didn't say take half your M&Ms and double them, correct? It was based on chance, right? It was based on chance. Who had their first roll not add anything to it? 1, 2, 3, 4. So 4 of you had nothing change for your first one. 3 of you had something change. Did anyone have exactly on a roll, exactly half of their M&Ms turn up? Yes. Did that happen every single roll? No. So you might have one where it's like it exactly doubled. So there were times that it exactly doubled. But then there's times that maybe you rolled 8 M&Ms and only one of them turned up with an M. So the thing that changes about that, are we able to absolutely 100% put a B value in there?
Not really.
No, because this was constantly changing. Sometimes it was doubling. Sometimes it was just less than that. What we do know is that if we did an average, it would have to be greater than 0. Correct? So on this one, when chance is involved, we're not able to have an exact formula. We can approximate it. Depending upon your data, maybe you are a person that got really close kind of to 50% most of the time. Okay? Hopefully that helps us visually see some growth and decay in person. Okay. So how does this affect, we're going to go over 8.3, and then we're going to spend, I'm going to do about 10 minutes on that, and then we're going to spend the rest of the time on 8.4. Okay. As we were learning about growth and decay, it was all great to learn about how to grow, how to decay, but the practical application of that was interest, and you did some homework problems that involved interest. So we learned that interest was our starting value, our A value, now was called something specific. They called it your principal, and they started with a P, correct? And then your B, remember our B gets to have different things. We had 100% of what we started with plus whatever our interest rate, either plus or minus, because sometimes if it's depreciation, it was going down. And then our X value was now called something very specific called time. And that's what I wanted you to see on this. It was the number of times that you rolled it, right? The number of times that you cut it in half. So that always helps me remember that time is the same as X. It's the number of trials that we're doing, the number of times that we do it. So we have this great interest formula. Said sometimes if our interest was going up, say it was going up by 6%, 0.06 times however many years. There was something that we started changing, and who remembers what this was? The N.
It's annually in days.
Correct. The number of times that it got compounded or it got broken up into something. So we can think of it overall. If I have a solid year, especially if we're looking at interest, they give you an annual percentage rate. Over the whole year, this is how much you will earn. But if I say once a year you come to me and I'm going to take whatever you have, I'm going to figure out the interest and I'm going to pay you interest for that, then that's super simple, right? But if I say every 3 months come to me and I'm going to pay you a portion of that interest, then you're not getting paid one time a year, you're actually getting paid 4 times a year. And so each time that amount grows, and as we've seen with exponential interest, we want, or exponential growth, we want new stuff added sooner than later. Because when we have our graph, the more that we add up front, the faster this grows, correct? So we want to be adding every single time I have a chance to add. I want to add a little bit more to it. And so we learned that if it was quarterly, we had to divide our interest rate by 4. And then we were also multiplying our time times 4, because instead of having 1 time, they were adding it 4 times. So that's why we have it in, like, our total amount, this was our total for the year, is now being dispersed 4 separate times. So it needs to be 4 separate times. They're paying me 4 times. If it was daily, it was 365 times, right? We're taking our interest, we're dividing it up into 365 days. But that means I got paid 365 times, right? So that's why it's in both the bottom and it's in the top. This is how many times they're paying me. This is how much I'm getting paid each time. So we have to divide, then we have to multiply 4. So what happens, this is daily, what happens when it's called continuously compounded? That means every minute it's changing. Every second it's changing. Every millisecond it's changing. It's continuously compounding. It's that ball that's now rolling over. This number starts getting really, really close to infinity, right? And we don't have a way to write that in an actual, like numerical form.
Solvable form.
Yeah, which means we also have a number really close to infinity up here. So that whole process of continuously compounded, they work it out and it becomes an E. Let me see if I can move this down. It becomes the E, which is called Euler's number. He's the guy that figured it out. When you do great things, you get stuff named after you. Okay, Euler. So Euler's number is this E, and it is a specific number, okay, that's pretty average, close to like 2.17, okay? But when we get that continuously compounded, it takes the place of all of that rate part, plus our percent divided by, infinity. So it takes the place there, and it becomes that E. And then now we have our rate times time is up at the top. Okay? So this is continuously compounded information. On your calculator, you actually have an E. There's an E button. And so it's taking that Euler's number. It's kind of like pi. It's a special number. The thing that you need to know about it is one, that it's from Euler. That's always important. And you need to know that it is for continuously compounded equations. The thing that happens with it is that it basically is just like, it works the same as a regular variable. So if I have e squared times e to the x, my bases are the same, so I would add my exponents. Okay? If I have e squared raised to the third, what do I now have? Power, e to the power, what?
E to the power 6.
E to the sixth. Okay, it is simply an another variable. I'm just going to try to see what I have for you for homework over that. Okay, if we have (1/4) e to the negative 2 raised to the third. Right? Exactly the same. We could basically kind of replace this in our brain as an x. Right? So now I have 1/4 raised to the third, and I have e to the negative 2 times 3, negative 6. Right? If we simplify 1/4 to the third, gives us 1/64. And where does this go for a negative? It goes from the top to the bottom, so it now has to be on the bottom. Remember, if it doesn't have a fraction there, it really is a fraction. So we work with e with the exact same exponent rules that we used if we had an x value. Okay? When we are graphing e, okay, it graphs, and we're matching stuff, it graphs just like saying, this is a base that I know. All it is a constant rate. So if I have 2e to, let's see. What do I want you to do? 2e to the x. This would be like 2 times 2.17 to the x. Okay? So my starting place is still 0, 2. On that one would be our y-intercept. I have a certain constant rate. It's bigger than 1, so it's going to be some growth. Right? It would start at 0, 2, and it's going to grow up that way. Okay, so don't let the e kind of freak you out. It's just a number, and if you want to replace the actual number in there, you can do that too. But if you're doing, there's a section that I have where you're just simplifying the expression, use it just like a regular variable. So think of it just like x.
Wait,
And
so do we really know what the graph looks like then? All we know is it goes up, but we don't know how it goes up.
Okay, so let's look at this one. Y equals 3e to the 0.5x. So this is where it's important. You're always going to want 2 points. Okay? So where does it start? What do we definitely know? When x equals 0, y equals what? 3. This is always your starting point. Okay, as long as we didn't have anything else added. If x equals 0, it's turned this whole point here. Right? Then we can say Like if x equals 1, we have 0.5, which is really 1/2 on that. And you'll work that out on your calculator. There's an E button. You can just do 0.5, or leave it as 0.5, and put the E button. Do you have it
Yeah.
on your? Yep, and then times 3.
Wait, why times 3?
Well, because that's this first part.
Oh, yeah.
And then it gives you 14.8. All right. So when E is 1, or sorry, when X is 1, then your Y value is 14.8. We can also look at it going backwards. The great thing about this, a lot of times you can put in a negative number and go backwards. What I like you to do on that one, there are some matching ones, and I'll post a video specifically about it as well to cover it more. Is we can often go backwards, or like you can put in -1 in this value, and then divide and get a better one. But for the graphs, you always know exactly what your starting point is. And then for the other one, you're going to use your calculator to find one more point. Right? If we had, let's look at this one. So we know it has to be growth because our E value is greater than 1, but we can grow different ways, right? Where are we starting? Well, initially we're starting at 0, 3, correct? But we've shifted our graph by what? 2 along the y-axis. So wherever we started, I'm going to shift. This is a k value. So I'm going to do -2. So I'm not starting at 0, 3. I'm really starting at 0, 3, -2, 0, 1. So when you're matching graphs, you're going to go, oh, I already have to start at 0, -1. Right? And then we would plug in a value and solve. Then you might plug in the number 2 into that. Solve it with your calculator to get your next one. But use your y-intercept that you know in any k values or any x values to change your starting point. So if we had the same one and I did, let's do positive x -2 plus 2, I would know I have changed it 2 and then this down 2. So I started from 0, now I'm at 2, so now my point's over here at 2, 1. The way I like to do it is I like to always write my initial y-intercept, this 0, 3 in this case, and then put my h and k values right underneath it. So if my h value is -2, I'm going to do +2. My k value is -2, and then I'm going to add those together to get my new point. It just makes it easier to just stick it right underneath my original y-intercept, and that gives me my new starting values. Does that make sense? If you want to keep it in order. All right, so not much on that. We're just going to simplify our e's, and we're going to look at some graphs just to identify them. Okay, so the next thing, this is a assignment that you guys have. I will post a video on how to do that because I don't want to take class time right now for it. This is, we're going to have, you have 2 different cars. So just real quickly, you do have 2 different cars. You have a car that you're going to take a loan out on, and then you have a car that you're not going to take a loan out on. So for both of them, they're both going to depreciate at the exact same rate. So for both of them, you're going to have a decay formula. Now, for the car that you didn't take a loan out on, the money that you put in it just stays in it. For the car that you did take a loan out on, it needs to have a interest growth rate. you're gonna pay more than you actually paid for it, correct? So the car with the loan will have both a growth formula and a decay formula for it. And I give you all the information for that, but I'll do a specific little video so you guys can check on that one. Okay, so logarithms. If we have, I'm gonna switch up here. If we've now learned our exponential functions, we know there has to be that opposite, right? Logarithms are the opposite. It is confusing, right? We'll just throw it out there. It can be very, very confusing. So there are a couple of little steps that I follow. I call it the log roll. Anyone ever watch those cool like axe shopping competitions and stuff? The guys, that's where I got it, like the log roll, where you're on it, okay? It feels like you have a slippery footing sometimes, okay? But if we have y equals b to the x, so we have some base raised to the x, there's got to be a way to undo it, right? Because we always have an inverse. How would we write the inverse for this one? Who has a guess? What do we do to find the inverse?
That would be b over 1. No, x to b root.
We switch the x and the y,
Oh. Ooh.
right? But then we're going to have to solve for y again. Okay, so that's how we would write the inverse. Remember, inverse just means we switch x and y, but we have to solve for it. So then we're like, whoa, it's an exponent. How do I solve for that? Okay, this is where our logarithms come in, all right? I'm going to leave that up there. Okay. We also know a couple of special things. We know that every inverse, the inverses, when they are multiplied times each other, they equal the identity, right? So if we have these functions and we start combining functions, they're going to equal x. That's what they turn out to. So we have our original form where it's an exponent, and then we have this secondary form where it says log. We're actually going to write the word log, and it has a subscript. So it's going to drop down b to the x. So it almost looks like we have taken this base with a superscript and just transferred it where 1 is now a little bit lower. Do we see that? Oops, I put the x instead of the y. Okay, so in this one we have a base with a superscript, this one we have a subscript with another. Our base stays in the same place. The base stays at the beginning, both times. Right? And I wrote up here, one of the hardest part about logs is actually writing and deciphering them. So I'm going to go through the log roll and explain what it actually means. When you have log of something, and we're going back and forth, there's going to be 2 rules. I'm going to put these side by side. If it started with log, you're going to drop the log. Okay? If it didn't start with log, you're going to write the word log. Okay? Everyone clear on step number 1? Okay. Step number 2 is you're going to write 3 blank lines. And they look kind of in the similar space. They're not in order. It's down, up, down, down, up, down for 3 blank lines. And there is an equal sign at the end of that H. So everyone have this. Before you do anything, this is what you write. All right? We have to have our template. Once you have your template and your template is accurate, it's just plugging in numbers. Right? So if I have log 5 or 1, we're going to put we're going to learn how to plug these numbers in. Okay, so for this one, it has log, which means I would drop the log, and I'm going to do 1, 2, 3. This one doesn't have log, so I'm going to write log and do 1, 2, 3. Right? We good there? Now, you always start left to right, and we're going to do the log roll. We're going to start at our base, and we're going to roll around and end. We can't end on the same value. So if we started at the first one, we're going to roll around and end on the second one. Right? Here, we're going to start. I want to have it the wrong direction. Change this. Okay. We always have to start at our base, and we're going to roll around and end. So there's our log roll. Okay. Now, we follow our line, and we're going to plug in whatever we come to. So what do we start with first? B. What do we come to second? X. What do we come to third? Okay. On this one, what do we come to first? B. Okay. Did we get the same thing? They look the same, they should match. Bx to the y, bx to the y, log b, base y, by x. There. Okay? Let's do this one at the top. We have log, we would drop it. We're going to start at the 2. Log roll around. So we're going to start with 2. Y, 3. Okay? On this one, start here, roll around, 2, 8, 3. Everyone's sufficiently confused.
There would be a log in the equation.
What?
Is there going to be a log in the equation?
Yes, so because we have to undo them, remember? So if we have exponents to undo them, we have to use logs. Right, so we're finding we're going back and forth or rewriting them different ways. Right? So, to rewrite them, what it is really telling us, these are 2 ways to write the exact same thing. Just like when we learned that we could say the square root of 2, or we could write it as 2 to the 1/2. Correct? They mean the exact same thing. They're just written 2 different ways. So these values mean the exact same thing. It's just written 2 different ways. Sometimes you're going to have a log. Sometimes you're not going to have it. And you need to know, what does it mean? When we knew with our exponent that we have some base raised to a power, so it's our exponential growth, equals a number. So when we're looking at logarithms, we want to ask ourselves, we have a base, and the number here at the end is called the equivalent value. You'll see that term or hear me use that term, the equivalent value, which means that's what it was equal to. So when we work with a log, because I followed around, I had bx equals y, what base raised to some power equals y? So in this case, I had 2 raised to what power equals 3? That's not a good one. Let's do 8. There we go. So if I have log 2, 8, it might just say that, log 2, 8. It will often not have that equal sign in it. You can always put equals what? Equals y, equals sad face, whatever you want it to be. We read this as 2 to what power equals 8. And that's because we've started with our log roll and we've gone around. So here's our variable. I used x. Okay. 2 to the x equals 8. For me personally, I can figure this out. Because I can rewrite, if I have 2 to the x, I can rewrite 8 as 2 to the third. So if my bases are the same, I know my exponents would have to match. Or I can practically go 2, how many 2's equal to 8? 2, 4, 8. Okay, 3. I know that x equals 3. It's easy for my brain to figure it out in this direction. It is very difficult for me personally to figure out on the log ones. So I often rewrite them as an exponent because that makes more sense to me. That's going to be a personal preference for you. If like you can look at this and go, oh, I've got 2 to some power and that equals 8. I know that 2 to the third, so my x has to be, my missing component has to be 3 in that one. They mean the same thing. Does everyone understand how to do the log roll for it? Okay, let's look at this. Okay, so let's take your boards and let's just practice. We've got a couple of minutes. Let's practice on these. How would you rewrite?
That is true.
How would we rewrite that first one?
2 to the 5th power equals 32.
2 to the 5th equals 32. Excellent. So I'm going to log roll around. I had log, so I'm going to drop it. Right? So it's not going to be, I'm start at the 2. My next number I come to is 5. And then I have 32. Is that true?
Yes.
Okay. Fantastic. How would we write that one?
Log 5 to 1 power equals 0.
Okay. Yes. So we had 5 to the 0 equals 1. We're going to log roll around, and we're going to put them in other. So we have 5 first, then 1, then 0. 5, 1, 0.
Why do you have to put log?
To undo it.
Because it's called logarithm. Like that's the actual, it'd be like sine, cosine, tangent. Like it is a specific operation. Okay. So what about the bottom one?
1/2 to the negative first power equals 2.
Okay. Is that accurate? What is negative 1
It's going to go to the bottom.
mean I do to this?
Flip it up.
Yeah, you'd have to do the whole thing in the bottom, right? And do we divide by fractions? Nope, we flip them. Yep, so we've got 2 equals 2, so it's true.
Well,
Okay, and then what about the other one? We would need to write the word log. What's the first number we come to? The second number?
2 to the 32 equals 5. That's not right. Oh yeah, it's not. Well,
Okay.
I don't know.
So, in this case, this is not 2 raised to the 32.
Yeah.
Okay? It is base of 2, and our equal value is 32. Okay? So this isn't 2 raised to the 32. Those are placeholders that are giving us specific information. Like, this is your house, and that's McDonald's. You know, like there are specific locations for it. So base 2, it's equal to 32. How many of those do I need? That gives us our 5. All right. So there are a couple of values that are important to know, and we went over one of them. We know that any number raised to the 0 power equals 1, correct? It doesn't matter what number I have. So I'm going to do any base raised to the 0 equals 1. So how would I write that as a log? Of my base, log of my base, what I'm going to log roll around. I start with b, my next number is 1, so my is equal to 0. So when we are looking at our logs and our exponents, anytime you have the log and your equivalent value is 1, the answer will always be 0. Because the only way you can have an exponent value end up being 1 is to have it raised to the 0. Does that make sense? Okay, what if I had 3 to the x equals 3? X would have to equal what? X would have to equal 1. So if I wrote that with log roll, I would say log 3, next number I come to, 3 equals 1. We know that's, I would say x, but that way we know it's actually a 1, right? So anytime my base matches is equal to my equivalent value, the answer is going to be 1. So we can say if I have log b to the b, my base and my equal value match. Anytime these match, my answer has to be 1. Those are 2 rules that it is important to memorize. Okay? You can memorize them, or you can practically think my base raised to the 1 is going to give me itself, right? That's the identity. Or my base raised to a 0 is always going to give me 1. These are 2 values that you need to have memorized. Okay? On your calculators, you only have log of a base 10, and that will be next week that we will learn how to change our bases. Okay? Let me check your homework.
I don't.
What?
Mine just says log and there's a parentheses.
Yes, because when no base is written, it actually means 10. It's that unwritten 1. Right? Why would they use 10? What is the base 10 to any power? You just add zeros, right? Scientific notation, it actually doesn't change the equation, it just changes where the decimal place is. That's why they use 10. Because multiplying by 10s is just changing decimal places. So it's actually not changing our thing. Okay, let me